All right, today we're diving into something called GraphMind, and a really fascinating idea. What if we could actually teach an AI how to think? So, here's this puzzle, right? How can an AI write stunning poetry, or even help you with your code, but then totally bomb a simple logic puzzle? We've all seen it happen. You give a large language model, an LLM, a problem it's never seen before, and it just falls apart. It's kind of like a brilliant student who's only memorized the textbook but can't actually apply the knowledge. So what's really going on under the hood? Well, there's actually a name for this. It's called LLM brittleness. And it's really the heart of the problem. It hints that what we're seeing, what looks like real reasoning, might just be, well, extremely sophisticated pattern matching. The AI isn't thinking its way through the problem from first principles. Nope. It's just digging through its massive memory for the closest thing it's seen before. And when you give it something genuinely new, it just breaks.
So this brittleness got some researchers thinking. They had this really radical idea. Instead of just cramming an AI full of more and more data, the entire internet, what if we could go back to basics? What if we could train its fundamental reasoning skills? Like, what if we could build a kind of cognitive gym, a place to teach it the absolute core mechanics of how to think?
And welcome to that gym. It's a place called Graph Problem Reasoning, or GPR. Now, for a second, let's forget all the messy, complicated stuff from the real world. Just picture this, a simple, abstract world made up of nodes, you can think of them as dots, and edges, which are just the lines connecting those dots. The big idea here was that this super clean, logical world would be the perfect training ground, the perfect place to teach an AI universal problem-solving skills that hopefully it could then use anywhere. So, what's on the workout plan in this GPR gym? Well, the AI isn't doing bicep curls, it's training its brain. For example, it learns logical reasoning by figuring out if a path in a graph ever circles back on itself, like cycle detection. For topological reasoning, it learns about structure, like finding the shortest path between two nodes, basically what your GPS does every day. It even learns how to be super systematic, trying to find a path that hits every single node just one time. It's this whole taxonomy of reasoning, a full-body workout for the AI's mind, designed to build those core thinking muscles.
Okay, but you can't have a gym without equipment, right? And for this cognitive gym, they needed a ton of it. So they built this massive, custom dataset called GraphPile. And when I say massive, I mean it. We're talking 10.9 billion tokens. That's just an insane amount of data, all focused on these graph problems and their solutions. This was no weekend project. This was a truly monumental effort.
But here's the thing. GraphPile wasn't just a giant, messy data dump. No, it was carefully, meticulously structured. It was built on what they call 4 pillars, and each pillar was designed to teach the AI a different way to think about a problem.
So the first 2 pillars are chain of thought and program of thought, and they're a really powerful 1-2 punch. Chain of thought gives the AI the why, the step-by-step logic in plain English, just like how a human would explain it. Then program of thought gives it the formal how, the actual executable code to get the job done. So the model learns both the human-style reasoning and the perfect machine-readable solution.
But the really novel part, the component that's a total game changer, is called trace of execution, or TOE. Seriously, this is the secret sauce. See, it doesn't just show the AI the finished code. Instead, it shows the dynamic process of that code running. It's like a slow-motion, frame-by-frame replay, showing exactly how all the variables change at every single step.
And here's a perfect example of what that TOO data looks like. The AI sees something like, okay, after visiting node 4, the list of visited nodes is now 0471, and here's the path I took to get here. It's not just seeing the final answer. It's learning the dynamic process. It's internalizing that when I do this, that happens. It's learning the actual cause and effect logic of how an algorithm works. That's a huge deal.
So, you've got the cognitive gym, this massive data set, this cool new training method. It all sounds great on paper, right? But here's the million-dollar question. Did the workouts actually pay off? Did training this AI on a bunch of abstract dots and lines actually make it smarter when it came to completely different problems out in the wild? And the answer was a huge, resounding yes. It absolutely worked. The model they built, called GraphMind, didn't just crush graph problems, it got way better at things it was never explicitly trained on. Look at these numbers. Its ability to reason about code shot up by over 46%. Its logical reasoning improved by more than 33%. This wasn't just memorization, these were real, transferable skills.
Okay, that's amazing, but it naturally leads to the next question, doesn't it? Which part of the training was the most important? Was it the chain of thought, the program of thought, or was it that special trace of execution data? The only way to find out was to do an ablation study, which is just a fancy way of saying they started taking pieces of the training data away to see what would happen.
And what they found was absolutely fascinating. So, just as you'd probably guess, when they removed that trace of execution data, performance on code reasoning took a nosedive. It dropped by 11.5%. That confirms it. TOE is super important. But then, look at the bottom of the table. Something really weird, really counterintuitive happened. When they took out the data from real-world graphs, performance on things like math and logic didn't go down. It actually went up.
Yeah, you heard that right. Let me just repeat it because it's the big twist. To make the AI better at pure abstract reasoning, they had to remove the data from the real world. Wait, what? How is that even possible?
Well, the leading theory is this. For learning pure abstract reasoning, all the messy details of the real world, the specific names of airports in a flight path or the titles of papers in a citation network, that's all just noise. It's a distraction. The model might waste its energy trying to make sense of those details instead of focusing on the clean, underlying logical structure of the problem itself. It seems that for learning pure logic, a pure dataset is best.
Now hold on. This doesn't mean GraphMind is now the one AI to rule them all. There's a trade-off. In becoming this super specialized expert at complex reasoning, it actually got a little bit worse at some general tasks, like summarizing a block of text. This is a known issue in AI called catastrophic forgetting. So think of GraphMind not as a replacement for your everyday LLM, but more like a highly specialized consultant you call in for the really tough problems.
And that right there points to a really cool potential future for AI. Maybe the goal isn't to build one single giant AI that's a jack of all trades. Maybe the future is more like a team of specialized AIs working together. You could have a manager model that routes tasks. It sends the simple stuff to a generalist AI, but when a really gnarly logic problem comes along, it knows to pass it over to an expert reasoner like GraphMind.
And that leaves us with a pretty profound question to chew on, doesn't it? Is the key to building smarter AI really just about feeding it more data, just scaling up bigger and bigger? Or is the answer something more subtle? Is it about pedagogy, about us becoming better teachers, about carefully crafting the right kind of data to build those fundamental bedrock skills? Maybe the next breakthrough isn't just about teaching an AI what to know, but finally, teaching it how to think.